Okay, thank you all for coming for the second feature. Today we have Lieutenant John Kidd, and John has a very impressive resume so far, so the future is just going higher and west. He started his hydrographic career at the Atlantic Hydrographic Branch in Norfolk, Virginia. In addition, he did his bachelor's at Old Dominion University in Norfolk. Yep. Norfolk. Graduated from Ocean, Earth, and Atmosphere in 2011. From then, he's been hopping on almost all the NOAA fleet, the OCS fleet at least, the Rainier, TJ, Fairweather. And not the Fairweather. No, only the Hassler. One day. Okay, one day doesn't count. Doesn't count. And joined CCOM as a master's student in 2015. Now we're going to see his defense, and after he finished his master's, he already has been assigned to become the ops officer on the Hassler. But as we know, things can be changed, but hopefully, no, it's final. Thank you. Thank you. Okay. Without further ado, John will present his research on performance evaluation using a terrestrial laser scanner, specifically Velodyne VLP-16, on the ability to detect surface features. Do you want to explain the timing again, or? Oh, sorry. Thank you very much. Same. We're going to have 40-minute presentation where, unless there's a clarification question, we'll move forward the presentation. Then we'll have a 20-minute session where first the committee will ask questions. After that, it'll be open to the general public to ask questions. And after that, we have our private session where we ask a few more fun questions. And at the end, the decision is made.
Great. Good morning, everyone. Thanks for coming out. It's actually a pretty impressive showing. So today I'm going to be talking about a performance evaluation of the Velodyne VLP-16 system, which is a terrestrial laser scanner. And we're going to be using it for surface feature surveying. So first up, wanted to go through an outline real quick. We're going to be talking about, I'm going to go through an introduction of what is surface feature surveying and give a background. Then we're going to talk about a technology overview, what are terrestrial laser scanners, how they work, and then go right into an instrument characterization of the system. Talk about an internal reference frame validation, characterizing the uncertainty with that angular separation. Also looking at the uncertainty of the range estimates for the scanner, and also looking at a data density evaluation. And then we'll look at some field data that I collected this past summer and end with a couple discussion points. So first up, what is surface feature surveying? In the NOAA world, we call it shoreline survey, and that's a simple definition we could use as mapping of the features at the intersection of the land-water interface. So here's a chart of southern Maine here. This is the approach to Portsmouth Harbor. And you can see a lot of complexity in this area. There's a lot of different feature types. There's islands. There's little islets out here, rocks that are above the surface, below the surface. There's some pile points out here. There's even a pier. So there's a lot of things that need to be mapped in this area. So who conducts shoreline survey? The National Geodetic Survey Remote Sensing Division conducts the initial surveys and captures the information about the majority of the main features here, like the contiguous shoreline here, which is mapped to mean high water, and most of the major items here. But after that, our Office of Coast Survey field units, they conduct shoreline verification surveys where they go out and look to verify, disprove, or even find new features that are out there. So how do we conduct shoreline survey? The Remote Sensing Division uses these two remote sensing techniques, airborne LiDAR bathymetry, which we heard about this morning, and also photogrammetry. These are aircraft-based remote sensing techniques. What about the Office of Coast Survey? So I'm going to be referring to their current methods that they use as traditional shoreline survey, which kind of looks something like this. It's these hydrographers are perched on a rock using an alidade and plane table, and they first position themselves on the earth and then position the item of interest or the target of interest. Now, today we obviously have the use of GPS and computers to help us, but we're still taking discrete measurements on these targets by using magnetic compasses and laser range finders to get a relative horizontal positioning, which will correlate to the GPS position. And also for the vertical positioning, sometimes we're using visual estimation. So, and we're using pencil and paper to notate all this information down, and also the GPS cookie trail, if you will. So what standards are we surveying to? For that, we look at the International Hydrographic Organization Standard 44, Standards for Hydrographic Surveys. And for surveying the coastline, we're obviously going to be in very shallow water, so we're only dealing with special order and order 1A surveys. For the horizontal positioning, we're looking at, for topography significant to navigation, the positioning needs to be better than 2 meters is what we're shooting for horizontally. But vertically speaking, to be able to determine if the feature is above the water or below the water at the tide datum, mean low, low water, we're going to be looking at total vertical uncertainty. Here's the equation we use to determine the standards for that, where this depth-dependent factors are zeroed out, right, because we're surveying features at the surface. So we're looking only at the A here, which is 1/4 meter plus or minus for special order surveys, and plus or minus 1/2 meter for order 1A surveys. So what has NOAA been doing to try to improve on these traditional shoreline methods? So over the past decade, we've been looking at using mobile laser scanners to improve these practices. In 2008, Captain Rick Brennan, the gentleman in front of the room, kind of started this off. He looked at the Regal LMS system. Here is the data set from that study. And 2012, Katrina Wiley, a PS, a physical scientist that just graduated from UNH a couple of years ago, she used the Trimble landmark system. Here's the data set from that study. And in the conclusion of those studies, they basically found that using laser scanners compared to traditional methods, it took a lot less time to complete those surveys. The data was accurate. They actually found a lot more features out there. It was safer because you're collecting the information on these targets from a safe distance. It's a remote sensing technique. But they also saw that it was very cost prohibitive using these survey grade laser scanners, which cost anywhere from $50,000 to $200,000. So recently, a new class of laser scanners has come available on the market, industrial grade laser scanners. In 2015, VTAD Pradith, in collaboration with CCOM and NOAA, looked at the HDL32 system here on the left. This scanner has 32 different lasers which rotate 360 degrees, and they were able to successfully integrate it onto a survey platform and also create a driver, high-pack driver, so to be able to integrate it with our acquisition system. For my study, I'm looking at the VLP-16, the guy on the right here. We chose this sensor because of its lower cost than compared to the HDL32. Also, its small size, and also the weather resistant capabilities it has. I'll talk about this in the next couple slides. To do a comparison of these two different scanner types, survey versus industrial, I picked the original 2 survey grade scanners that we looked at previously, and also the 2 industrial grade scanners. And just to clarify things, the survey grade laser scanners are designed to complete surveys to high precision, to map things with high precision, to create a 3D point cloud. These industrial grade scanners were created essentially for specifically these Velodyne sensors for the automotive industry for target detection and avoidance. So we're intending to use them for something that they weren't initially intended to be used for. But to go down these different categories, we can see that the industrials are much more inexpensive. The survey grade ones have a lot farther ranges. Accuracies are actually about in the same playing field, the data output for these industrial grade scanners are a lot higher compared to the survey grade. That's because they use a little bit more inexpensive laser elements in them, so they can stack a lot of the elements inside. They're all working in the infrared spectrum. Beam divergences are usually a lot smaller for survey grade scanners, so you'll get a smaller footprint out at farther ranges, and they're all class 1 eye safe. So my goal in this study is to evaluate the use of a low-cost industrial grade mobile laser scanner if it can be used for completing shoreline surveys with performance that can meet survey requirements for charting purposes. That's what we're trying to accomplish here. And to do that, I conducted several experiments in a well-controlled environment to conduct an instrument characterization and also to verify the specifications from the manufacturer, Velodyne. And to do that, I used the Chase Ocean Engineering wave tow tank just on the other side of this wall here. It's a 36-meter long tank with a tow carriage mounted on top that can be positioned along this rail here with millimeter accuracy. So that kind of functioned as our control for the reference frames. The instrument characterization we've looked at, like I said in the introduction, was the angular separation between each beam, and also the range uncertainty and a data density evaluation. And after we conduct the instrument characterization, we mounted it on the research vessel Gulf Surveyor here, UNH's new boat, and collected a data set this past summer in Portsmouth Harbor. And we'll look at the data set from that at the end of the show, the PowerPoint. So to go through a technology overview, terrestrial laser scanners come in all different shapes and sizes with different laser characteristics, different frequencies and pulse repetition rates. But I'm going to be talking about all these, the technology overview as it relates to the VLP-16. So all terrestrial laser scanners have these 3 components here. And for the VLP-16, this is what their laser ranging unit looks like. It's a ceramic hybrid board. With on one side they have the emitter electronics, and the other side is the detector. The optomechanical scanning device is actually just a mechanical scanning device. These laser elements are stacked on a center rotating stave, and they rotate 360 degrees like this. So there's no optical component like another terrestrial laser scanners. They don't have rotating mirrors. It's just purely mechanical. And the control and data sampling unit is this Velodyne interface box, which is connected to the scanner by a 3-meter cable. So just like laser range finders, the terrestrial laser scanners use a 2-way travel time to calculate the range to a target. For these scanners, they're using the lasers that are in the near infrared spectrum, so 903 nanometers. And again, they're using 2-way travel time, so by multiplying the time interval elapsed by the speed of sound and speed of light in air, which is about 300,000 kilometers per second, you can calculate the range. But for the terrestrial laser scanners, the VLP-16 has 16 laser beams that are spread within a plus or minus 15-degree vertical field of view, and they rotate 360 degrees to give you a nice 3D point cloud. The angular separation between each beam is 2 degrees, shown in here. The accuracy in the user manual is stated as plus or minus 3 centimeters typically. It's IP67 rated environmental protection, which is an ingress protection, meaning that basically it's protected against dust and it's splash proof. With a firing sequence of 18.2 kilohertz per each laser, we get about 300,000 data points per second. Question I get often is it eye safe? Is it safe to look at? And yes, it's class 1 eye safe, so you can look at it with the naked eye and even standard magnifying optics like binoculars. The laser itself is 903 nanometers, so we're not going to get any kind of water penetration, which is fine for us. We're not looking to measure the depth of the water. We're only getting information above the water surface, so surface features. The beam divergence for this laser is 3 milliradians, which at its maximum range of 100 meters represents a beam diameter of about 30 centimeters. So how does all the parts fit together on a mobile survey platform? So just like our echo sounders, the laser scanner needs to be told where it is on the Earth's surface at all times, and also at what precise direction it's pointed. So the roll, pitch, yaw directions that it's pointed. So by using the GNSS positions and timestamps with the IMU accelerations and rotations and the scanners measured ranges, angles, pair all that together, you get the final geolocated location of the target of interest. So this is an image modified from Amin Habib representing the laser scanner geolocation equation down here at the bottom. So the end goal here is to calculate the vector from the mapping frame to the target, which is this vector x sub g, which is calculated by summing together these three vectors here, which x sub 0 is the position of the vessel, the GPS position of the vessel represented at the IMU body frame. P sub g is the sensor offset measured before the survey from the IMU to the scanner, and this row vector here is the range from the scanner to the target. Now you also need to have the rotations for each of these reference frames. So the R sub yaw pitch roll is the angular offsets, or the angular displacements measured by the IMU. The R sub delta omega delta phi delta kappa is the bore sight calibration angles between the IMU body and the laser scanner body. And finally, the R sub alpha beta is the azimuth and elevation angles measured by the laser scanner. So my first instrument characterization experiment we conducted was to verify the 2-degree elevation angle separation between each beam. Again, this is from the Velodyne user manual. They have it typically 2-degree separation. So we were interested to see how accurate were those mounting angles. They don't publish any uncertainty values to this metric, and also to see if that spacing is indeed uniform throughout the field of view. And this is important to know because this is a direct component of this geolocation equation. This beta here represents this angle, which if this is wrong, it's going to propagate all the way down to an error to the coordinate of the target. So to look at this, we used the wave tow tank. We mounted the scanner vertically. So throughout all my experiments, I'm usually mounting the scanner vertically, but just to be clear, when I say azimuth and elevation angles, I'm talking about how Velodyne uses them. So the azimuth angles here is the rotation 360 degrees up and down, and the elevation angles is the separation of the beams left and right here. So the scanner was mounted vertically above a high precision rotating compass, accurate to about 0.04 of a degree, which was mounted on top of a level tripod at the edge of the tow tank. The target we chose was a narrow strip of aluminum, which is highly reflective, and we positioned it at around 8 meters, which the laser beam footprint at that range corresponds to the width of that target. So the idea was we were going to mechanically calibrate the scanner by rotating it back and forth across this target and take measurements of the data that are just within the specular area of this target and look at the intensities. So when the laser was perfectly aligned with the target, we would see the highest intensity, the peak intensity, which is interpreted to be that the laser scanner target is perfectly aligned. So here is a plot of one specific setup that we had. We had to do this in 4 different setups. This was centered around the -11 degree beam here. And on the y-axis, we have intensity. So each data point here is the average intensity for that setup. And as you can see, the data points make nice distinct peaks at specific angles. And as you can see, -9 and -7 degree, we're registering some offsets here. So the cumulative offsets we have from the -15 degree working right are represented in this plot with the angular offsets on the y-axis. As you can see, at the -5 degree beam, we measured a offset of about 1/10 of a degree. So that was the worst case scenario that we had. Taking this worst case scenario of 1/10 of a degree offset at the maximum range of 100 meters, that represented a horizontal offset of about 17.5 centimeters. So we have our rock out here at the maximum range of 100 meters. An error due to the 1/10 of a degree error that would cause a horizontal error of about 17.5 centimeters, which is still well within the 2-meter requirement. We also wanted to characterize the uncertainty with those elevation angles. So to do that, we looked at the spread of the elevation angles, this beta angle here. So to assess that, we used this simple equation here. We had the z coordinates of all the data, and the r was known for that experiment. It was static, so we took the mean of that, and to rearrange the equation. So we had inverse sine the z, which is the coordinates of the points on the target, over the range. And this is the spread of the elevation angles that we got for each beam, which on average was about 600th of a degree. So that was the uncertainty with those elevation angles that we had, which again, out at a maximum range of 100 meters, taking the worst case scenario, if it was 600th of a degree off, that represented a horizontal error of about 10.5 centimeters. So adding that to our previous 1/10 of a degree error, we get a horizontal uncertainty of error of 28 centimeters, still well within the IHO spec of 2 meters. Next, we wanted to verify the range uncertainty for the scanner. Again, back to the user manual, they state that it's typically plus or minus 3 centimeters. We wanted to do this as a function of range to the target, the incident angle of the target, so from what angle you're scanning the target from, and also the nature of the target. Was it rough? Is it smooth? We chose these 4 different targets because they covered a wide range of superficial roughnesses. From left to right, we had whiteboard, which was analogous to like a freshly painted surface or a metal buoy, something that was highly reflective. A wooden target to represent like a wooden piling or a wooden pier, concrete for a concrete pier or other structure, and then sand for a sandy beach. We wanted to characterize the range uncertainty on these targets to make sure that the scanner was performing uniformly across all these different target types. So again, we're back on the Wave tow tank, except this time we're using the tow platform to adjust the range of the target. So we mounted the scanner vertically directly to the tripod at the edge of the tow tank, and the target is now on the platform, which again we're adjusting the range. Below the target, we mounted a rotating compass so we could adjust the target left and right to adjust the incident angle of the laser beams as they intersect. But here's the ranges that we used and the incident angles that we use. And at 75 degrees incident angle at the maximum range of the tow tank, the footprint of the laser beam was still on the target, so we didn't have any edge effects. For the alignment procedure, we basically use like a ranging technique like a mariner uses to navigate down a channel. We compared the real-time horizontal coordinate of the target we got from the scanner. We compared that value to the computed horizontal location of the target. And if those didn't match, we knew that the scanner target pair weren't aligned very well, so we adjusted until those values matched. So here's some of the plots that we were generating from this experiment. These are for the wooden target, and as we click through, we're going to be increasing the incident angle, and this is a range at 5 meters. The data points here are individual points on the target from the laser scanner, and they are colored by intensity. So I'm going to start this animation, and as it goes through, you can see as we increase the incident angle, the intensities are getting smaller and smaller. That's due to most of the laser light being forescattered and less of the light coming back to the actual sensor. You can also see that the target appears to be getting closer to the scanner, so the scanner is here to the left, This is a side view of the target. The target seems to be getting closer to the scanner. That's because as you increase the incident angle, the beam footprint is intersecting the target at a closer range. So to look at the spread of this data here, here are 4 different plots. This is for the whiteboard target, wooden target, concrete target, and sand. So we're increasing superficial roughness this way. Each colored curve is represented by the different incident angle that the target was at. We have range on the X and the 2 sigma confidence intervals of the spread in the range direction on the Y-axis. As you can see, there's kind of an inverse relationship between superficial roughness and the 2 sigma confidence interval. So the sand target, it was ranging, the performance was really well for this whiteboard target at the furthest range and highest incident angle. It actually performed relatively poorly. But averaging all these data points at the maximum range of the tow tank of about 30 meters, we get a 2 sigma confidence interval average of plus or minus 1.5 centimeters, which is well below about half the specifications. Because of the tow tank was only 30 meters long, we couldn't actually test the scanner at its maximum range. But just out of curiosity, we generated lines of best fits for all these curves and extrapolated out to 100 meters, averaged those data points all the way out at 100 meters, and we resolved exactly at the plus or minus 3.0 centimeter confidence interval. So that matched the specifications. Now that experiment was only done for 1 laser beam, but as a sanity check, we conducted an abbreviated experiment verifying all the other laser beams. So we have minus 15 all the way out to 15 here. We did this only on 1 target, the aluminum target, at 1 range and 1 incident angle, the normal incident angle. And we found that all the other laser beams were performing as expected, also well below the plus or minus 3 centimeter advertised accuracies. So next we have data density potential. So the user manual for the VLP-16 has it represented in the time domain. So about 300,000 points per second, which was a little difficult to interpret because I'm used to thinking about things in the spatial domain, you know, like 5 pings per sounding to populate a node. So we were curious to see what kind of data density we could get from the sensor, 5 points per square meter, 5,000 points per square meter. As you imagine, there's a lot of different factors that you have to consider when trying to understand this. This is a laser scanner simulator that Dr. Farad Aaron helped me create to mimic the physical characteristics of the scanner. So we're accounting for the beam. The laser scanner had 16 beams. We're accounting for pulse repetition rates, scanning frequencies, mounting angles of the scanner. So if you mount the scanner to scan horizontally, the beams that are at the horizon are going to make vertical stripes of data as the boat moves along. So if your 1 meter square box is in between those 2 beams, you're not going to get any data within that box. But is straight up vertical mounting angle the best configuration? We were curious to see about that. And also rotation rates, so how fast the laser scanner is rotating. Vessel speed we can control with the simulator. We can even introduce a little bit of vessel motion caused by wave activity, so roll, pitch, and yaw. Factors we didn't consider in this simulation was any kind of radiometric losses due to absorption and scattering of the light in the atmosphere. Also the reflectivity of the target, we didn't consider that at all. The beam divergence of the laser. So in this simulation, we're getting best case scenario, 100% of the data coming back to us. So here are the final results of a vessel passing a target at 4 knots at various ranges and various sensor configurations. So the left plots are with the scanner mounted 90 degrees, so vertical. The right plots is with it mounted 45-degree pitch angle forward. You can see the diagonal stripes it's making. We're starting at 10 meters and going out to 100 meters. And for this setup, we're rotating at 1200 RPM. The blue box represents the 1 square meter, which we use to count the number of pings inside. shown here, which will be shown in a table format in the next slide. So as I click through, we're increasing range. As you can see, the data density is decreasing as we're getting farther and farther away. This makes sense. This is 80 meters, 90 meters, and all the way out at 100 meters. This is the same set of slides, except now we're rotating at 300 RPM. So the vertical spacing here of the points is a lot closer. Again, as I click through, we're going to be increasing in range. 50 meters. And you got 100 meters. This is the tabular results of the simulator. Like I said, we can see an obvious inverse relationship between the ping number, the points within the box, and the range to the target. So as the scanner is getting further from the target, we're getting less points, and that's due to an inverse square relationship. We can also see that the oblique scans are, for some reason, getting a lot more pings inside the box relative to the vertical scan configurations. And we're pretty sure that's because just the physical shape of the box. With it mounted 45 degrees forward, we got about 1.4 times more than with it mounted vertically. That's just because, like I said, the physical shape of the target hypotenuse of a 45, 45, 90 triangle is square root of 2, roughly 1.4. So that explains that. So to compare the simulated results with real-world results, we collected a data set out at the UNH pier face. Here is our target of interest. It's a vertical, relatively flat, smooth surface, easily identified in the data set because we had a lot of nice features on the pier, these bollards here and these vertical rub rails. So we collected lines of data mimicking the same configurations we had in the simulation. So from 10 to 100 meters at these various different sensor configurations. Here's a picture of the scanner mounted on the flying bridge of the RV Gulf Surveyor. Vertical mount, so the bow of the boat is here to the left. Here's with it mounted with a 45-degree pitch forward. For processing, I manually cleaned out all of the data that were outside of this box, so we're just looking in between the rub rails here. Imported the data into MATLAB, and to align the 1 square meter box with the data, I calculated the plane of best fit using least squares approximation, and then used that normal vector to rotate the data to align with the 1 square meter box. And that's what we use to count the points within that box. So here's the type of the results from the field validation. You can still see the inverse relationship between point count and range. You're getting a lot more variability for a specific range to the target. See down 900 here and 1,300 points in that configuration. That's due to vessel motion, we're thinking. So as we're passing by the target, this was done in Portsmouth Harbor, which has kind of squirrely currents. So it's kind of hard to maintain the boat at that specific 4-knot speed. And also the boat is yawing back and forth. So that's explaining this high variation. But an attempt to compare these field validation results with the simulator, I calculated the percent errors, so experimental versus theoretical. And so lower values here in this table represent a closer match to the theoretical. And as you can see, we have some strong players here at 20-meter range and 300 RPMs. We had a close match with experimental versus theoretical. Out in the oblique side, the best match we got was about 11%. So the reasons why we don't get a good comparison here, especially at farther ranges, was because in the simulator, we weren't, like I said before, we weren't accounting for any radiometric loss. So scattering, we weren't accounting for reflectance of the target and the beam footprint. Also, we didn't introduce any vessel motion in the simulator, so that wasn't accounted for either. In the experimental, we had a lot of vessel motion to deal with. So to summarize the instrument characterization that we did, had showed you the results from an internal reference frame validation. We saw that we observed a maximum offset of 1/10 of a degree with an associated uncertainty of 600ths of a degree. We then looked at the range uncertainties and saw that at least within 30 meters, we had a range uncertainty of about plus or minus 1.5 centimeters at various incident angles anyway, and different targets. And then finally, we looked at a data density evaluation, and which was only done in the strongest return mode. The scanner also has a dual return function. But we saw that at extremely close ranges, we had extremely dense data of about 1,800 points per square meter. And even at farther ranges, 50 or 60 meters, we had about 400 points per square meter. So moving on to the field performance validation, we mounted the scanner on the RV Gulf Surveyor and basically did a quick survey of the Portsmouth Harbor. I'm just going to show you some point clouds resulting from that. This is whaleback light just outside Portsmouth Harbor. And just to correlate some features here, we have some rocks just off of the feature here. And you can easily see them in the data set here. And these pictures were taken at the same time the laser data set was acquired using a DSLR camera that was triggered as we passed by. Another feature here, you can easily see this was at a range of about 50 meters. It was 70 meters to the lighthouse. And we kind of passed a little bit further from the back side of this, about 95 meters. Here is Fisher's Island inside of Portsmouth Harbor. This is Pepperell Cove in the background. Again, just to correlate some features, we have a rock out here, getting good coverage on. We didn't get any data on this beach back here. Here's the backside of whaleback light. You can see 3 little rocks just barely poking above the water surface here, and they're actually kelp covered and getting submerged and unsubmerged by the water surface. And we're still getting good data points out on those features. Again, there's some rock features out here. We passed by this U.S. Coast Guard ship. That'll be interesting to show, and also the security gate here with this lattice structure. At the farthest, we didn't quite get the lattice structure here, but we were starting to pick it up once we got close enough. We saw the dock line of the ship. That was at a range of, I think, about 50 meters. Here's the Memorial Bridge, first bridge you'll come to in Portsmouth Harbor. Here's what it scanned up. Here's Sarah Long Bridge, which unfortunately doesn't exist anymore. So I can't check my numbers.
That's the best result.
The I-95 bridge, which is much higher up. It's a fixed bridge, and we were still able to even get points all the way up there. The bottom of the bridge was 50 meters away. We were also interested to see if we can get data on overhead power cables that cross the channel. This is a back channel. This is the Navy base, Portsmouth Naval. We were able to get data points on these kind of features also, which is really nice. Further up the river, north of the I-95 bridge, we have cables that are a lot taller up because we have a lot of cargo ships coming back and forth, and we were even able to get good data points on this. The cable diameter up there is 1.8 centimeters, and it's aluminum conductor steel reinforced cable. And that was about 50 or 60 meters up. You can see the radar reflector balls, the top cables we got, but we didn't get the cable that connected those radar balls. Which leads me to a discussion point. What could we use the scanner for additionally? So this is looking at a concept of verifying air gaps. An air gap is basically the vertical distance between the lowest point of a target, a feature that crosses the channel down to the water surface at a specific tidal height. So for NOAA charts, it's mean high water. That was a picture of the USS New Orleans passing under the famous Huey P. Long Bridge, which is in the southern Mississippi River, and she passed under with a margin of about 2.1 feet. So it's very, very close. This is a very important thing to be able to chart. These are the features that we surveyed, the overhead features that we surveyed, and we have our charted vertical clearances here in meters at mean high water. here's our surveyed vertical clearances, again, meters at mean high water. And the difference is charted minus surveyed, so positive numbers, meaning we surveyed a lower height. So it looks like we're resolving some discrepancies on our charts here. The Army Corps of Engineers have begun conducting their own surveys. They contract out using this company here, using a survey grade mobile laser scanner to survey 22 different bridges in 4 days in the upper part of the Mississippi River. And they saw an average discrepancy of about 5.2 feet and a maximum discrepancy of 11.6 feet lower for this specific bridge. They're also have plans to conduct more surveys in the future. They're doing 2 initial surveys of bridges this next year. And they're submitting these reports directly to the Coast Guard, the bridging office, the charting authority that publishes the vertical clearances for these features. And the Coast Guard is taking this information and updating their light lists, which allows the Army Corps to update their charts. I'd like to just acknowledge a couple of players, acknowledge that the work that I did here was a part of a bigger work that's being conducted. HIPAC, thanks VTAD for helping me integrate the systems. The boat, they're constantly integrating this technology in new and inventive ways. Citco, Rabin helped me with a couple experiments down here. They're working on bore sight calibration procedures up there. Here at CCOM, I think we're going to continue looking at characterizing the TPU for these kind of sensors. Coast Survey and Development Lab implemented these scanners on NOAA's charting vessels this past year. Thanks to Paul Lavoie, helped me fabricate a couple of the laser scanner mounts. Captain Emily Terry, Captain Ben Smith, and Dan for expertly navigating the vessel. And my thesis committee, and also my wife and family for their support. Questions?
Very good job. Captain Armstrong?
So when you compared the simulation data density with the field target results, it seemed that the differences were greater in the oblique scanning area, and it seemed to be consistently different and different by a significant amount. Why would you think that might happen?
Well, with an oblique scan, so the relative width of those beams as they intersect is going to be smaller relative to a vertical scan. So the causes of vessel motion are probably a lot more predominant effect because of that. It was kind of hard to interpret those data sets because of the vessel motion. We tried to time it at slack tide, but obviously we can't do all that data acquisition within a narrow period of time. So we had a lot of vessel motion to consider.
So what would your recommendation be for the mounting arrangement? Would you recommend the 45-degree angle or the vertical?
For the simplicity of the bore sight calibration procedure, currently we're not able to roll, y'all pitch the sensor in that configuration without it. Those angles are just displacements from the vessel's reference frame. So if you roll a little bit, the scanner, those offsets are translated into the other axes. So it's kind of difficult to patch that in. So just for ease of installation and quick deployment, I would just suggest mounting it vertically.
Okay, and how many, in that mode, the number of actual targets, of actual hits seemed to drop off with range to where at one point you got 100% difference, right?
Yeah, absolutely. We didn't get any.
But you also showed a number of field examples where you were considerable distance. What would you recommend as a sort of operational limit of distance for using the system for shoreline verification?
So like an effective extinction range, like at what range can we anticipate to be able to get enough data on a target out? I would say around 60 or 70 meters, it starts to become a little scant out there. You can certainly get data at farther ranges, but it's going to be hard to interpret that, hey, that's a rock out there, because you're going to have a few points on that target, which if you acquire photographs at the same time, it would be easier to interpret, or if you overlaid RGB values on that laser data set, you could help interpretation of that data set. But in order to get a good amount of data on, I would say 60 to 70 meters.
So my questions are also along the same line as Andy Armstrong. So as far as I know, these units are being used in NOAA vessels right now. So what is the mounting angles? That's what I'm wondering. Like, do they mount vertically or horizontally?
They're mounting them vertically. They followed some guidance from the Army Corps and developed a mounting bracket that's on top of the overhead of the survey vessel, and they're mounting it vertically. I'm not sure if they've actually welded those mounts in place yet. They were kind of just strapping them in temporarily to see how they were working, but I believe they moved forward with that.
So would you recommend to change to oblique angle, horizontal angle?
No, I think I haven't seen it in action yet, but I have no reason to suspect that it is not working well.
Another question I have, so when you talked about the data density, so what is the practical data density you get in real life in survey conditions, or what is the minimum number of data to survey for like feature detection?
What is the minimum amount of points I would need on a target?
Yeah.
I guess it depends on the target type, right? If it's a rock that's barely poking above the water surface, I would want a lot more points on that relative to like a vertical pier, where if they were a little bit scattered, a little bit less dense, it could still determine that that was a planar target, a vertical planar target. Ironically, you're going to get a lot more data on that vertical surface and probably less data on the rock. So, but within 50 to 100 points probably. And at 50 meters, like we saw with the field results of the data density analysis, we were getting about 400 points per square meter. Again, that was a vertical target, so it's kind of best case scenario. But
Thank you.
So again, continuing on the same operational level first. First steps, how do you see it mounted and unmounted from vessels? Do you need to do a calibration based on the results of your study?
at least a rough bore sight calibration, yeah. We don't need to get to hundredths of a degree alignment. The calibration process I used was basically driving a box around a dayboard, a fixed dayboard outside of Portsmouth Harbor, and using the geometry of the vessel and the dayboard, able to adjust the scanner that way. So it wasn't, you know, hundredths of a degree accurate, but it was certainly good enough, especially to meet IHO spec.
Okay. And then after collecting the data, how do you think of interrogating the data? You talked about kelp and you talked about the specular targets.
Mm-hmm.
So you might lose at angles. So how, following what Firat asked about the number of points, do you see any kind of logging done on the field, or just processing based on just the point cloud you have available?
So the current use of these scanners in the field, how I interpret it is, or how I've been told, is that they're acquiring data points real time. So as you see this point cloud come in, they're looking outside the boat, they see that's a rock out there, and they correlate it with the rock feature in the real-time point cloud. HiPAC has a function where you can query that target and get the least depth on that target, which is outputted to a 000 file directly. So it's currently they're not doing any post-processing with this data set. So it's not really adding any post-processing time in the back end.
Last question here, and this is extrapolating from your study going forward. What happens when you have multiple surveys over the same area? Do you see them fitting well with each other, or do you get some bore sight or some other issues going on?
So the better your bore sight calibration angles are and integration to the survey vessel, the tighter comparison you're going to get, yeah.
Your field measurements, how did they?
They matched up well, especially the pier face, running different lines at different ranges and stuff with the right bore sight calibration angles. They matched up well.
Open to the public.
Is it affected by sunlight intensity at all?
It is a lot, actually. If the sensor face is pointed directly at the sun, you're going to get a lot of blowout because of it's just saturating the sensor. So you'll get, I should have had an image showing this, but big wedge of data going up towards the sun, which is pretty easy to clean out, right? The data isn't usually behind a feature. So if we were surveying a bridge and the sun was behind the bridge, that would be problematic. You kind of have to think about that when you're out in the field, how you run your lines.
Does the amount of sunlight on a target affect the number of returns coming back and the accuracy?
I didn't look at that specifically. I would think, unless the target itself was a specular target like the water surface, then yeah, that would definitely affect the scanner. But if the target scatters the sunlight enough, and it shouldn't very well affect it.
But you can elaborate what happens when it saturates the sensor, because you saw the results, what offset you saw.
Yeah, so when I scanned the aluminum target, which is really bright target at normal incident angles, I saw a really saturated intensity return coming back to me, which also registered as a closer range, probably because the digital signal processing, it's picking a point that I'm not sure how they choose the point for the range, if it's the peak of the intensity or if it's some other point, but we saw a range artifact due to a saturation.
Really?
Yeah. Well, I have a few questions. One of them.
I don't get to pick the people asking questions.
I have three.
Next defense.
You can answer in order. First of all, you mentioned that it's more important to look at the shallow rocks rather than the vertical wall, right? And that suggests that it would be better to mount it obliquely, right? So if you mount it obliquely, then you have better look at the shallow rocks and the same look at the vertical wall. If you mount it vertically, you have less points looking at the rocks. So, and that means that maybe it is still better, even though calibration is more difficult. You are getting more information with the oblique mounting of the sensor. That's the first thing. Second, do you know how the weather conditions affect the range measurement? Because I can imagine that light is propagating differently in rain. And third, you have a rotating part, mechanically rotating part, and that means vibration.
Yes.
Is it affecting anything, or vibration is negligible?
I'll let you answer by order or any.
I'll go inverse, I guess. So for the vibration, there probably is effects of the vibration. So for the angular uncertainty and offset measurements that I did, I only did at one specific azimuth. So maybe doing an assessment of different azimuths would kind of shed some light on if there's a vibration issue going on. I suspect there is some vibration. I mean, when you hold that unit in your hand and it's spinning, you feel it.
Right. Because
yeah. So yes, there's probably effects of that in there. I'll go back.
But you did not investigate how this affects the accuracy of measurements.
I didn't know. The weather component, yes. Like in Matt's discussion, he said, you know, if you fly ALB surveys when it's foggy out, you're not going to get very good data. You might not get any data back because the light reflects off all the water particles in the atmosphere and absorption. So in heavy rain, I definitely wouldn't suggest conducting these operations. The fair weather collected some data in Alaska, where it's always nasty weather. And they were able to get penetration through a light fog. So it's possible, but I would definitely try to shoot for nice sunny days.
Sure, but does it mean that when the weather is not nice, it's not worth even doing this?
I guess that's an operational consideration, right? If you have to go tomorrow and this is the only day you have to acquire the data, you're going to do it, right? But if you can wait a week, it'd be better to wait. And for the mounting angle, I'm not sure if we got the geometry right. So when you're mounted vertically on the boat, this is the scanner, we're scanning 360 degrees this way. The 45-degree pitch forward, I guess I'm doing like a John Hughes Clark dance up here, but
so suppose you are mounting it vertically and it rotates around.
that's
like that.
horizontal.
Horizontal. So, but if you mount it with some angle, it looks more.
I agree. So the higher up, the lower the incident angle will be, the better chance you have on getting some returns off of that target. Absolutely.
But that relates to the height of the mounting from the vessel and doing, now we have the John Hughes Clark dance. If when you're scanning and you're starting to move forward, so you will hit that target, it depends on the speed. So you, if there's some incidence, you will slow down for that to get more density along the horizontal line. Okay, Captain Brennan?
So to follow on with Yuri's question, I'm curious if, because most of the commercial sensors out now, they actually have two.
Yep.
And they're oriented. So any thoughts on the value of that, particularly to get it in the coming and the going direction?
Mounting both, yeah, yeah, absolutely.
Two of those Velodynes in one installation.
So if you mount it in different configurations, you approach on the target from one side, you would get coverage on the other, on that side. If you go back around it, if the other scanner was pointing in the other direction, absolutely you would get data on the back side of it. These survey grade ones usually only have one laser, so I think that's why they usually implement it that way. But yeah,
I just wasn't sure if the fact that you had multiple gives you the same effect.
yeah, exactly.
The angles that they're rotating at are much greater, and so you're getting them at a much different, significantly different angles than just.
And we have 16 different beams, right? So if we're going under a bridge and we're mounting, we're scanning vertically, the plus or minus 15-degree beams above us is going to look something like this. So the forward beam is going to scan the bridge from this direction. When we go under the bridge, the back beam is going to scan the other side of the bridge. So it kind of gets around that.
You showed an equation in the beginning to go from the reference frame of the moving platform to the stationary platform. I think that's valid only for stationary platforms moving at a constant velocity. So if your IMU does output accelerations, you can extend that. And the reason I'm mentioning this, you can improve the numbers on the chart on table 31, because now you mentioned it was difficult to keep the boat at a constant velocity, when it's, being hit with waves and so forth. It's quite easy to extend that equation to include the changing parameters.
Will you include that in the rotating method?
Yeah. So you can
Like
have,
predicted where.
think about the launch. If you're trying to go at a constant velocity, everything's valid. But if you're accelerating or decelerating, that's a source of error because you're not accounting for that change. And you showed that on the chart on slide 31. You said there was a wide discrepancy among the values. There's the equation at the bottom. And you can extend that to include accelerations if your IMU outputs it. That's just, something to consider. You don't have to do that.
Right.
Mr. Ice?
So you listed your angular uncertainties in the context of the total allowable horizontal, but that was only for the laser. As far as the other contributions to the total propagated uncertainty, what does it say about the requirements for the positioning of the vessel and angular alignments and lever arm accuracies and those kinds of things? Did you consider those at all?
No, that was just purely sensor contributions of that uncertainty. Obviously, the end coordinate of that target, it's going to have components from uncertainties from various sources, like the foresight calibration, the vessel, the offset survey. So that was just from that one component.
Do you think our typical offset surveys would be accurate?
I think so, yeah.
What about positioning of the vessel?
Certainly positioning the vessel.
It have to be ERS though.
We did collect with RTK and for that data set, so yeah, definitely URS.
Well,
I have a question from the internet and our own Scott Loranger. I think that you probably touched on the answer to this in a couple of the other questions, but taking a step back and more of a general question, Scott's asking what you think the biggest impediment to the use of these systems as a common mapping tool might be.
Well, previously it was the cost, right? I mean, we just couldn't justify the cost. So now that these sensors are really affordable, this unit was only $8,000. It's really to scoop it up, implement it on the boat, and start to use it. So, and we've seen that all of our OCS vessels now, I think all have them and are being implemented now. There's a lot of plans for other people to use it here at CCOM. The ASV people plan on using it for target detection and avoidance, and they're very popular nowadays.
and just to elaborate more, Vitad and I, back in the day, were discussing the different options, and about $100 and even $50 LiDAR systems, but the ones on the range of $6,000 to $12,000, you have like only free at the moment that I'm aware of, that meet these requirements. And actually Velodyne were the most forward going here with HiPAC, giving some proprietary knowledge, which allowed it to integrate it, which allows it to implement it on the ships. Matt,
yeah, I was just gonna ask about like the shadowing effect of the laser beam. So like some of the rock detection you're trying to do, a lot of the feature was shadowed. Is that gonna like hinder your ability to map those features, or do you just gonna have to do laps around them?
So it's a cartographic question, right? We're trying to ultimately pick the highest point of that rock. So if the laser intersects, if the highest point of that rock, the laser intersects it, and you get a data point on that point, then we've achieved what we were trying to do. But if there's a higher point on the backside that's blocked by the front, you're not going to get data on it. So yeah, that would be a consideration. But that's kind of a cartographic side of things.
last question. Val.
Okay. So my first one is, maybe I missed it, but you measured the horizontal effect of the beam pointing angle, but did you also measure the vertical effect as you had it mounted, like how well their encoder is for positioning the beam?
I didn't get to that, no. And like you just said, it has an azimuth encoder, so it registers when it passes a certain point, and I didn't look at that, no.
And my second question was, your images of the data are beautiful.
How much cleaning did I do?
Yeah, how painful is that? How much the sort of volume of data like compared to what we're used to with sonar systems, and how much culling did you have to do? What was that like?
It can be a lot of data. In HiPAC, you have the ability to disable certain beams, so if you only wanted to acquire with one beam, you could. The scanner has a dual return mode, so you can be collecting twice the amount of data, which HiPAC seems to be choking on right now anyway. It slows down a lot. As far as cleaning, like I said, with the blowout from the sun, it's usually easy to find and clean out. It's just a quick swipe and it's gone. Even the returns off of the water surface, as the sun bounces off the water up to the scanner, you'll get a streak of data that are below the water surface, and it's easy to clean out. If you're passing boats and they're like stemming with you, you'll get a streak of data off to the port side. You just kind of have to be cognizant of what's going on out there. And like I said, NOAA's finding or querying the data out in the field real time, so they're not actually needing to post-process it as of yet. So.
Good. So thank you again to John